There's a cloud near the center of our galaxy that contains enough alcohol to keep every person on Earth supplied for billions of years. It drifts roughly 26,000 light-years from where you are right now, hidden behind layers of dust and ancient starlight that our eyes cannot penetrate. The alcohol inside this cloud is real. It is ethyl alcohol, the same molecule found in wine, whiskey, and beer, floating freely through space. I find it remarkable that the universe, in its quiet way, has assembled something so familiar in a place so impossibly far from any human experience. This region is called Sagittarius B2, and it sits near the dense, crowded heart of the Milky Way, where stars cluster in extraordinary numbers. The cloud stretches across roughly 150 light-years, a span more than 1,000 times larger than our entire solar system, from end to end. Within that volume, astronomers have detected quantities of alcohol that defy easy comprehension, enough to fill 400 trillion pints if collected. And yet, no one will ever collect it, because this alcohol is spread so thin that a single cubic meter contains only a few molecules. You're listening to The Drowsy Astronaut, and over the next while, we're going to drift through this cloud slowly, explore what's inside it, and consider what it tells us about how the universe builds complexity in places that seem, at first, impossibly cold and empty. This is a slow journey and is designed to help you relax while exploring the wonders of our universe. If you'd like, you can let us know in the comments where you're listening from tonight, wherever in the world that might be. And if this kind of slow science storytelling feels right to you, a like or subscription helps others find it too. So without further ado, let us begin. The location matters in ways that become clearer the longer you consider it. Sagittarius B2 orbits within a region known as the Central Molecular Zone, a ring of dense gas and dust that surrounds the supermassive black hole at the galaxy's core. This area contains more raw material for building stars than almost any other place in the Milky Way. Packed into a relatively compact space, the cloud itself has a mass equivalent to several million suns, all of it slowly churning through gravitational currents that shape everything within. When astronomers first detected alcohol in this cloud, they were not looking for it specifically. They were simply listening to the radio signals coming from that direction. Every molecule, when it rotates or vibrates, emits light at specific frequencies that act like a fingerprint unique to its structure. The fingerprint of ethyl alcohol appeared clearly in the data, repeated across vast stretches of the cloud with unmistakable consistency. It was not a trace detection or a tentative signal. The alcohol was genuinely there, spread across distances that dwarf anything in our local neighborhood. The amount present is difficult to hold in a single thought. Estimates suggest the cloud contains approximately 10 billion liters of ethyl alcohol in its gaseous form, though that number changes slightly depending on how the measurements are interpreted. For comparison, all the alcohol humanity has ever produced throughout history would vanish into insignificance against this cosmic supply. The cloud simply has more, by factors so large that the comparison stops being meaningful and becomes instead a kind of quiet statement about scale. It is worth pausing to consider what this means, not in practical terms, because there is no practical application, but in terms of what the universe apparently does when left to its own processes. No one designed this cloud or intended for alcohol to form within it. The molecules assembled themselves through chemistry that operates without supervision, guided only by the laws that govern how atoms meet and bond. This is not a distillery, it is a consequence of physics, playing out over millions of years in conditions that seem hostile to anything complex. The temperature inside the cloud hovers around -150 degrees Celsius in most regions, though some areas near forming stars grow significantly warmer. At those temperatures, chemical reactions proceed slowly, if they proceed at all, requiring timescales that stretch across millennia. And yet the alcohol is there, which means something is working. Some process is building these molecules, despite conditions that seem designed to prevent exactly that. What makes Sagittarius B2 particularly interesting is not just the alcohol, but the fact that alcohol is only one of many molecules detected there. This cloud is unusually rich in organic chemistry, containing dozens of distinct molecular species that astronomers have identified over the past several decades. Some of these molecules are simple: carbon monoxide, water, ammonia, while others are surprisingly complex, built from 10 or more atoms arranged in specific patterns. The cloud, it seems, is not just making alcohol, it is making a great deal more. The detection of this chemistry has changed how we think about what space contains and what happens in the darkest regions between the stars. For a long time, the space between stars was imagined as essentially empty, a void, with occasional atoms drifting through, but nothing organized or interesting. Sagittarius B2 showed that this assumption was incomplete, that molecular clouds can build complexity without heat, without pressure, without anything that resembles the conditions we associate with chemistry. The cloud is a laboratory of a kind we did not expect to find. There is something quietly astonishing about the ordinariness of what exists there. Ethyl alcohol is not exotic. It is the compound that makes beverages intoxicating, the same molecule that fermentation produces when yeast consumes sugar. To find it drifting through space, 26,000 light-years away, assembled by processes that have nothing to do with biology or intention, suggests that chemistry simply happens wherever conditions allow. The universe does not reserve certain molecules for certain places. It allows them to form wherever the rules permit, and the rules apparently permit quite a lot. As we continue through this series, we will look more closely at what else the cloud contains, how those molecules form, and what they might mean for questions much larger than any single cloud. There is a great deal to explore within this region, and the alcohol is only the beginning, a familiar molecule that opens the door to much stranger chemistry. The next part will reveal what other molecules have been found drifting through this same vast space. The alcohol in Sagittarius B2 shares its space with a remarkable collection of other molecules, many of which would seem at home in a chemistry laboratory rather than the void between stars. Astronomers have now identified more than 50 distinct organic compounds within this single cloud, each one confirmed through careful analysis of radio signals reaching Earth. Some of these molecules are simple, built from just a few atoms, while others contain 10, 12, or even more atoms arranged in precise configurations. The cloud has become one of the most important sites in the galaxy for understanding how complex chemistry emerges in space. Among the molecules detected is methanol, which is the simplest form of alcohol and consists of just one carbon atom bonded to hydrogen and oxygen. Methanol forms more readily than ethyl alcohol and appears throughout the cloud in substantial quantities, serving as a kind of chemical stepping stone toward more complicated structures. It is toxic to humans if consumed, but in space, it simply drifts through the cold darkness, participating in reactions that build ever more elaborate compounds. The cloud contains enough methanol to dwarf any industrial supply on Earth. Also present is formic acid, which on our planet is the compound that gives ant stings their burning sensation and contributes to the discomfort of bee venom. In Sagittarius B2, formic acid exists as a gas distributed across enormous volumes, detectable by the specific pattern of light it emits when its molecules rotate. The discovery of formic acid in space was unexpected when it first occurred, because the compound seemed too complex to form without biological processes. Now we know that chemistry alone is sufficient. The cloud demonstrates this simply by existing. Acetic acid appears in the cloud as well, the molecule responsible for the sharp smell and taste of vinegar, familiar from kitchens around the world. Like the alcohol, acetic acid forms through reactions that require no cells, no enzymes, no biological machinery of any kind. The presence of this molecule in a cloud 26,000 light-years away suggests that the chemistry of everyday life is not particularly unusual in cosmic terms. The same compounds that flavor our food and sting our skin are drifting through the galaxy in quantities beyond counting. Perhaps more surprising is the detection of glycolaldehyde, which is the simplest sugar, a molecule built from 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. Sugars are essential to biology on Earth, forming the backbone of DNA and providing energy for nearly all living cells. To find even the simplest sugar floating freely in a molecular cloud suggests that the raw ingredients for life's chemistry are not rare, not special, not confined to planets with oceans and atmospheres. They form in the darkness between stars where nothing is alive and nothing intends for them to exist. One of the more curious discoveries in Sagittarius B2 is ethyl formate, a molecule that contributes to the flavor of raspberries and gives rum part of its distinctive character. The detection of this compound prompted some media coverage describing the cloud as smelling like raspberries and tasting like rum, which is technically true at a molecular level, but practically meaningless. No one will ever smell or taste this cloud directly, and the molecule is spread so thin that collecting any would be impossible. Still, the presence of ethyl formate demonstrates how specific and varied the chemistry within the cloud actually is. Formaldehyde drifts through the cloud as well, a molecule best known on Earth as a preservative and disinfectant, often used in laboratories and medical settings. In space, formaldehyde is a building block, a relatively simple molecule that participates in reactions, leading to more complex organic compounds. Its presence in Sagittarius B2 is expected given the other chemistry observed, fitting into a pattern of molecules that grow more elaborate over time. The cloud is not just holding these compounds, it is actively producing them through ongoing chemical processes. What unites all of these molecules is that they contain carbon, the element that forms the basis of organic chemistry and ultimately the basis of all known life. Carbon has a particular talent for bonding with other atoms in varied and stable configurations, which allows it to build molecules of tremendous complexity and diversity. The cloud is essentially a carbon chemistry factory, assembling compounds that on Earth require careful laboratory conditions or the machinery of living cells. In space, the same chemistry proceeds without assistance, taking only time and raw materials. The molecules detected so far are almost certainly not the complete inventory. Detection depends on having laboratory data for comparison. Scientists must know what fingerprint to look for before they can identify a molecule in space. Some compounds may exist in the cloud that have never been synthesized on Earth, making them invisible to current detection methods. Others may be present in quantities too small to distinguish from the background noise of cosmic signals. What we have found is likely only a fraction of what exists. Among the most intriguing detections are molecules that serve as precursors to amino acids, the building blocks of proteins and the foundation of biological structure. These precursors are not amino acids themselves, but they represent steps along the chemical pathway that could lead to such compounds under the right conditions. The cloud cannot produce life on its own. It lacks the liquid water, the stable surfaces, the protected environments that biology seems to require. But it can produce the raw materials, seeding future planetary systems with chemistry that took millions of years to assemble. The diversity of molecules in Sagittarius B2 has made it a kind of natural laboratory for astrochemistry, the study of how chemistry operates in space. Researchers use this cloud to test their models of molecular formation, checking whether predicted compounds actually appear in the expected quantities and locations. The cloud provides data that would be impossible to generate on Earth, because no laboratory can replicate the conditions of space over the necessary timescales. Every detection refines our understanding of what chemistry can accomplish without supervision. What strikes many researchers is not just the variety of molecules present, but the quantities involved. This is not trace chemistry, but chemistry occurring on a massive scale. The cloud is producing organic compounds in volumes that dwarf anything associated with individual planets or stars, spreading them across regions larger than our minds can easily picture. This chemistry is not happening in hidden corners or special locations. It is happening throughout the cloud, everywhere, continuously. In the next part, we will consider what else is occurring in this region, because Sagittarius B2 is not just a chemical cloud, but a place where new stars are being born. While molecules drift through Sagittarius B2, something else is happening within its densest regions. New stars are forming, pulling matter inward through gravity's patient work. The cloud is not just a reservoir of chemistry, but one of the most active stellar nurseries in the entire Milky Way galaxy. Deep inside its structure, pockets of gas have grown dense enough to collapse under their own weight, heating as they compress and beginning the long process of ignition. The chemistry and the star formation are not separate phenomena. They are connected, each influencing the other in ways that shape what the cloud becomes. Astronomers have identified several distinct regions within the cloud where star formation is particularly intense, labeled with names that describe their relative positions. Sagittarius B2 North, Sagittarius B2 Main, and Sagittarius B2 South represent the most active zones, each containing clusters of young stars in various stages of development. These designations sound clinical, but they represent extraordinary concentrations of energy and matter. Places where the cloud is actively transforming itself into something new. The stars forming here are not like our sun. Many of them are massive, burning through their fuel at rates that will exhaust them within a few million years. Massive stars live fast and end dramatically. But during their brief lives, they pour enormous amounts of energy into their surroundings, heating the gas and dust nearby. This heating affects the chemistry of the cloud, warming the ice-covered dust grains and releasing molecules that had been trapped on their surfaces. The alcohol and other organic compounds detected in Sagittarius B2 are partly a consequence of this warming. They form on cold dust grains and are liberated when nearby stars raise the temperature. Star formation and molecular chemistry are partners in this cloud, each enabling the other. The young stars in these regions emit not just heat, but also intense ultraviolet radiation, which can both create and destroy molecules depending on the circumstances. In some zones, the radiation breaks apart complex compounds, reducing them to simpler components. In others, it provides the energy needed to drive reactions that would not otherwise occur, building complexity rather than reducing it. The cloud is a dynamic environment, with chemistry constantly being made and unmade as conditions shift around the forming stars. Observations of these star-forming regions reveal structures called hot cores, compact zones where temperatures reach several hundred degrees above the surrounding cloud. Within hot cores, the chemistry changes dramatically, as molecules that are stable in cold conditions become reactive and combine in new ways. Many of the most complex organic molecules in Sagittarius B2 were first detected in these warm pockets, where the energy from nearby stars has transformed the local environment. The hot cores are small compared to the overall cloud, but they are chemically rich beyond proportion. The stars forming in Sagittarius B2 will not remain there forever. Over millions of years, they will clear away the surrounding gas and dust through their radiation and stellar winds, gradually dispersing the material that currently fills the cloud. Some of that material will be incorporated into the stars themselves, or into planets and smaller bodies that may form around them. Other material will be pushed outward into the broader galaxy, carrying the molecules assembled in the cloud to new locations far from where they formed. Star formation is also a process of redistribution, scattering chemistry across vast distances. Not all the matter in the cloud will become stars. Most of it will remain as gas and dust, cycling through the galaxy in ways that may eventually bring it back to another cloud, another site of star formation. The efficiency of star formation is typically quite low, meaning that only a small percentage of a cloud's mass actually ends up in stellar cores. The rest continues its slow journey through galactic space, participating in processes that operate over timescales longer than any single star's lifetime. Sagittarius B2 is part of this larger cycle, contributing material to the galaxy's ongoing evolution. What happens in this cloud today has echoes that will persist for billions of years. The stars forming now will eventually die, some in quiet fading, and others in explosive events that spread newly forged elements across space. The molecules assembled here will travel to destinations we cannot predict, possibly ending up on planets that do not yet exist, around stars that have not yet formed. The cloud is a moment in a process that stretches across cosmic time, connecting past chemistry to future possibilities through gravity and motion. Nothing here exists in isolation. The energy output from the forming stars also creates structures visible to radio telescopes, revealing the cloud's internal architecture in remarkable detail. Bubbles of hot gas expand around the most massive young stars, pushing against the surrounding material and creating shells and cavities within the cloud. These structures tell the story of what has happened over the past few 100,000 years. Which stars formed first, where they are located, how their energy has shaped their environment. The cloud carries its own history written in gas and dust. Among the stars forming in Sagittarius B2 are some that may eventually produce the heavy elements needed for rocky planets and complex life. Massive stars manufacture elements like carbon, oxygen, and iron in their cores, then distribute those elements through space when they die. The very atoms that make up your body were once inside stars, like the ones now forming in this cloud, assembled through nuclear fusion and scattered by ancient explosions. This is not metaphor. It is a factual statement about where the matter in living things originally came from. The connection between star formation and chemistry makes Sagittarius B2 particularly valuable for researchers studying the origins of organic matter in the universe. By observing this cloud, scientists can watch the conditions that lead to molecular complexity develop in real time. Or, at least as close to real time as observations across 26,000 light-years allow. The light reaching our telescopes now left the cloud around the time that the first Homo sapiens were beginning to migrate out of Africa. What we see is already history, though the cloud itself continues onward, without waiting for our observations to catch up. The presence of so many organic molecules in a region actively forming stars raises questions about what those molecules might eventually become. Some will certainly be destroyed. Ultraviolet radiation, stellar explosions, and the heat of forming stars will break apart many of the complex compounds currently drifting through the cloud. But others may survive, incorporated into the dust and gas that eventually coalesces into planetary systems. This possibility that molecular clouds seed new solar systems with organic chemistry leads naturally to questions about how we know any of this in the first place. The next part will explore the methods that make such distant chemistry visible to us here on Earth. Every molecule in the universe has a way of announcing its presence, though the announcement is so subtle that detecting it requires patience and precision in equal measure. When a molecule rotates or vibrates, it emits light at specific frequencies determined by its structure and composition, creating a pattern as unique as a fingerprint. By capturing and analyzing these patterns from distant sources, astronomers can identify what molecules are present without ever touching or seeing them directly. This technique is called spectroscopy, and it is the foundation of everything we know about the chemistry of Sagittarius B2. The light that molecules emit is not always visible to human eyes. In fact, the molecules in molecular clouds typically emit radio waves rather than optical light. Radio telescopes are designed to detect these long wavelength signals, collecting them with large dish antennas and processing them into data that can be analyzed for molecular signatures. The signals are extremely weak after traveling 26,000 light-years, requiring sensitive equipment and careful elimination of interference from earthly sources. The process demands time and attention, but the rewards are measurements that would otherwise be completely impossible. To identify a molecule in space, astronomers need to know what pattern to look for, which means the molecule must first be studied in a laboratory on Earth. Scientists create samples of specific compounds and measure their spectral signatures under controlled conditions, building a library of fingerprints that can be compared to astronomical observations. When a pattern in the data from Sagittarius B2 matches a pattern in the laboratory catalogue, a detection is confirmed. This seemingly simple process has required decades of coordinated work between chemists and astronomers around the world. Some molecules were actually detected in space before anyone had ever produced them in a laboratory, which created an interesting puzzle for researchers. In these cases, astronomers observed spectral patterns they could not immediately identify, forcing chemists to work backward, guessing what molecule might produce such a signature, and then attempting to synthesize it. The successful synthesis of these compounds confirmed the astronomical detections and expanded our understanding of what chemistry is possible in the cold vacuum of space. The cloud taught us about molecules we had never thought to look for. The radio telescopes used for this work are remarkable instruments, ranging from single large dishes to arrays of smaller antennas spread across continents. The Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and various other facilities have all contributed observations of Sagittarius B2 over the years. Each telescope has different strengths. Some are better at detecting certain frequencies, others offer higher resolution or sensitivity, and combining their data provides a more complete picture. The cloud has been observed by nearly every major radio telescope in the world. One challenge in molecular detection is that different molecules can sometimes produce similar spectral patterns, especially in crowded regions with many species present. Distinguishing between compounds requires looking at multiple spectral lines for each molecule, ensuring that the overall pattern matches expectations rather than just a single feature. This careful verification prevents false identifications and ensures that the catalogue of detected molecules is reliable. The process is conservative by design. Claims of new detections are scrutinized carefully before being accepted by the scientific community. The sensitivity of modern telescopes has improved dramatically over the past few decades, allowing detection of molecules present in smaller and smaller quantities. Early observations could only identify the most abundant species: carbon monoxide, water vapor, ammonia, while later work revealed increasingly complex compounds present in trace amounts. Each generation of telescope technology opens new windows into the cloud's chemistry, suggesting that our current inventory is far from complete. There are almost certainly molecules in Sagittarius B2 that remain invisible to current instruments. Temperature affects the spectral signatures that molecules produce, which means that astronomers can learn not just what is present, but also how warm or cold it is. By analyzing the relative intensities of different spectral lines, researchers can estimate the physical conditions in different parts of the cloud, information that would otherwise be completely inaccessible. These temperature measurements have revealed the hot cores mentioned earlier, distinguishing them from the colder surrounding regions through purely spectroscopic means. The molecules are messengers carrying information about their environment. Velocity information is also encoded in the spectral signals through a phenomenon called the Doppler effect, which shifts frequencies depending on whether the source is moving toward or away from the observer. By measuring these shifts, astronomers can determine how different parts of the cloud are moving. whether they are collapsing inward, expanding outward, or rotating around a common center. This velocity information reveals the dynamics of star formation in real time, showing how gravity is reshaping the cloud's structure. The molecules tell us not just what is there, but how it is moving. The sheer number of spectral lines visible from Sagittarius B2 makes it one of the most complex sources in the radio sky, sometimes described as a forest of signals. Each molecular species contributes multiple lines at different frequencies, and when dozens of species are present, the result is an intricate pattern that requires careful analysis to interpret. Specialized software helps researchers identify and catalog these signals, but human judgment remains essential for resolving ambiguous cases. The cloud speaks in a language that we are still learning to fully understand. What spectroscopy cannot tell us directly is how the molecules formed in the first place. Detection reveals presence, but not process. To understand the chemistry that produces these compounds, scientists must combine observations with theoretical models that predict what reactions should occur under various conditions. The observations test these models, confirming predictions or revealing gaps in understanding that require new explanations. This back and forth between theory and observation is how knowledge accumulates, slowly building a picture of cosmic chemistry. The next part will explore what those models have revealed about how molecules actually form in the cold depths of space. The molecules in Sagittarius B2 do not form in empty space, drifting atoms that happen to collide and bond by chance, because such encounters would be far too rare to explain what is observed. Instead, the chemistry depends on something much smaller and more humble: grains of cosmic dust, each one a tiny platform where atoms can meet and react over thousands of years. These dust grains are typically smaller than the particles in cigarette smoke, yet they are essential for building the complex molecules that fill the cloud. Without dust, the chemistry simply would not happen. Dust grains in molecular clouds are made primarily of silicates and carbonaceous materials, similar in composition to fine sand or soot depending on their origin. They form in the outer atmospheres of dying stars and in the aftermath of stellar explosions, then drift through space until they become incorporated into clouds like Sagittarius B2. Once inside the cloud, the grains are bathed in cold temperatures that cause any surrounding gas molecules to condense onto their surfaces. Layer by layer, the grains accumulate coatings of ice, primarily water ice, but also frozen carbon monoxide, methane, and ammonia. On these icy surfaces, something remarkable happens. Atoms that land on the grain become stuck, trapped by weak electrical forces, and held in place for extended periods of time. While stuck, they can encounter other atoms that have similarly landed. And if the right atoms meet, they can react to form new molecules that would never have formed in open space. The surface acts as a meeting place, dramatically increasing the chances that two reactive atoms will find each other and bond. The reactions themselves proceed slowly by any human standard, requiring conditions that persist for tens of thousands of years without interruption. An atom might land on a grain, migrate across its surface for centuries, and eventually encounter a suitable partner. A process that seems impossibly inefficient until you consider the timescales available. The cloud has existed for millions of years, and the dust grains have been accumulating their icy mantles for most of that time. patience is not a limitation here. It is the engine that drives the chemistry forward. Simple molecules form first, built from the most common elements: hydrogen, oxygen, carbon, and nitrogen. Water ice accumulates as hydrogen atoms meet oxygen atoms on grain surfaces, while methane forms when hydrogen finds carbon, and ammonia forms when hydrogen finds nitrogen. These simple compounds become the raw material for further reactions, providing the building blocks from which more complex molecules can eventually be assembled. The chemistry is hierarchical, proceeding from simple to complex in stages that each require their own timescales. More complex molecules form through reactions between these simple precursors, sometimes requiring energy input from ultraviolet radiation or cosmic rays that penetrate the cloud. When a photon or particle strikes a molecule frozen on a dust grain, it can break chemical bonds and create reactive fragments that immediately seek new partners. These energetic reactions build compounds that would not form through simple surface encounters alone, adding another layer to the chemistry occurring on each grain. The dust grains become sites of constant molecular creation, destruction, and reassembly. The key step that releases these molecules into the cloud occurs when nearby stars begin to form and heat their surroundings. As the temperature rises, the ice coating the dust grains begins to sublime, transitioning directly from solid to gas without passing through a liquid phase. The molecules trapped in the ice are liberated, released into the cloud as gases that can then be detected by radio telescopes on Earth. The alcohol, the acids, the sugars, all of them spent time frozen on dust grains before being freed by stellar warmth. This process explains why the most complex molecules are often found near young stars, in the hot cores where temperatures are elevated enough to drive sublimation. The cold outer regions of the cloud still contain ice-covered grains with molecules locked inside, invisible to spectroscopy until something warms them and releases their contents. The distribution of molecules throughout the cloud reflects this history, a map of where heating has occurred and where ice still remains intact. The chemistry is not uniform. It varies dramatically depending on proximity to sources of warmth. Laboratory experiments have confirmed many aspects of this dust grain chemistry. Using vacuum chambers and cryogenic temperatures to simulate conditions in molecular clouds, scientists create artificial dust grains, coat them with ice, and expose them to radiation to observe what reactions occur. The compounds produced in these experiments often match those detected in Sagittarius B2, providing strong support for the theoretical models. The laboratory cannot replicate the timescales of space, but it can demonstrate the pathways through which complex molecules might form. Some chemistry also occurs in the gas phase, without any involvement from dust grains, though this pathway is generally limited to simpler molecules. Ions, atoms or molecules carrying electrical charge, are more reactive than neutral species and can undergo reactions even in the cold, low-density environment of the cloud. These ion-molecule reactions build up some of the simpler organic compounds, which then condense onto dust grains and participate in further chemistry. The gas phase and grain surface chemistry work together, each feeding into the other. The efficiency of dust grain chemistry helps explain why molecular clouds are so much richer in organic compounds than other regions of space. Without the surfaces that dust provides, atoms would rarely encounter each other, and complex molecules would be vanishingly rare. The dust concentrates the chemistry, providing platforms where slow reactions can accumulate results over timescales that dwarf any human endeavor. This is chemistry at its most patient, building complexity, one reaction at a time across spans of time that begin to approach the age of the solar system. Understanding this chemistry matters because it shapes the raw material from which planetary systems eventually form. The dust and molecules in clouds like Sagittarius B2 will someday become asteroids, comets, and planets, carrying their organic chemistry with them into new configurations. What forms on a dust grain in the cold darkness may eventually find its way to the surface of a world where conditions favor further complexity. The next part will consider the cloud's location more carefully, how it sits near the galactic center, and what that position means for understanding its place in the Milky Way. Sagittarius B2 lies in a direction that human eyes cannot explore directly. Hidden behind such dense accumulations of dust and stars that optical telescopes reveal only darkness when pointed that way. The galactic center, the rotational heart of the Milky Way, sits roughly 26,000 light-years from Earth, and the cloud orbits within the crowded zone surrounding it. To reach the cloud from here, light must travel through thousands of light-years of intervening space, crossing spiral arms and passing countless stars we will never individually see. The distance is large enough that the light arriving at our telescopes tonight left the cloud when humans were still fashioning stone tools. The obscuration is almost complete in visible wavelengths, with interstellar dust absorbing and scattering optical light so effectively that the galactic center appears as a dark gap in photographs. Radio waves, however, pass through this dust relatively unimpeded, which is why radio telescopes have been essential for studying Sagittarius B2 and its surroundings. The cloud was essentially invisible until radio astronomy developed enough to detect it. A reminder that our picture of the universe depends entirely on what tools we have built to observe it. Different wavelengths reveal different realities. The region around the galactic center is unlike anywhere else in the Milky Way, characterized by extreme densities of gas, dust, and stars packed into a relatively small volume. The central molecular zone, the ring of material that includes Sagittarius B2, contains perhaps 5 to 10% of the galaxy's total molecular gas, despite occupying less than 1% of its volume. This concentration means that conditions in the zone differ significantly from those in the solar neighborhood where we reside. Everything there is more intense, more crowded, more dynamic than what we experience locally. At the very center of the galaxy lies Sagittarius A star, a supermassive black hole with a mass equivalent to roughly 4 million suns, exerting gravitational influence over everything in its vicinity. Sagittarius B2 orbits around this black hole at a distance of approximately 300 light-years, following a path shaped by the combined gravity of the central mass and the surrounding stellar population. The cloud is not falling into the black hole. It is orbiting around it, much as Earth orbits around the Sun, though on vastly larger scales. The orbital period is measured in millions of years. The journey from Earth to the cloud, if one could somehow make it, would take you first through the relatively sparse regions of the Orion Arm, the minor spiral arm where the Sun resides. Beyond that lies the Sagittarius Arm, a major spiral structure that wraps partway around the galaxy and adds additional material between us and the center. Farther still, you would encounter the Scutum Centaurus arm, and finally, the crowded conditions of the inner galaxy, where stars cluster so densely that night skies would never truly darken. The path crosses some of the most varied terrain the galaxy contains. Radio observations have mapped the gas between Earth and the galactic center, revealing a complex, layered structure that changes continuously along the line of sight. Some of this gas belongs to other molecular clouds, some to diffuse material that fills the space between clouds, and some to structures whose nature remains uncertain. The cloud we are discussing is just one feature in this intricate landscape, the one that happens to be most spectacularly rich in organic chemistry. Other clouds in the region contain their own molecules, but none match the diversity and abundance found in Sagittarius B2. The proximity of the cloud to the galactic center may partly explain its unusual properties. The environment near the center includes more cosmic rays, stronger magnetic fields, and more frequent gravitational disturbances than the quieter regions where the sun resides. These factors could enhance certain chemical processes or trigger star formation more readily, though the exact mechanisms remain subjects of ongoing research. The cloud exists in a more extreme environment than most molecular clouds, and that context likely matters. Gravitational interactions with other clouds and with the overall mass distribution of the inner galaxy affect how Sagittarius B2 evolves over time. Tidal forces stretch and compress the cloud as it orbits, potentially triggering episodes of star formation when densities temporarily increase. Collisions with other clouds can inject energy and turbulence, reshaping internal structures and possibly enhancing the chemistry through shock-driven reactions. The cloud is not isolated. It participates in a dynamic environment where neighbors and gravity constantly exert influence. The view from within the cloud, if one could somehow experience it, would be quite different from any night sky familiar to Earth-based observers. Stars would be visible in astonishing numbers, far more than we can see from the outer galaxy, though dust within the cloud itself would obscure the most distant ones. The galactic center would loom relatively nearby, its concentrated starlight creating a brightness unlike anything in terrestrial experience. But no observer has ever stood within the cloud, and none ever will. It remains forever beyond direct human experience. Understanding the cloud's position helps explain why it has been so valuable for astronomical research. The galactic center is one of the most important regions for studying the large-scale structure and evolution of the Milky Way. And Sagittarius B2 provides a window into conditions there. Every detection of molecules in the cloud tells us something about chemistry in extreme environments, about star formation in crowded regions, and about processes that occur throughout the galaxy, but are easiest to observe near the center. The cloud is a laboratory, positioned in one of the most interesting places the galaxy contains. What we learn from this cloud can be compared to what we learn from other molecular clouds throughout the Milky Way, revealing patterns that hold across diverse environments. Some aspects of the chemistry appear universal. Certain molecules form wherever conditions allow, while others seem specific to particular regions or circumstances. The next part will explore how Sagittarius B2 compares to other famous molecular clouds, and what those comparisons reveal about what makes this particular region so unusual. The Milky Way contains thousands of molecular clouds scattered throughout its spiral arms and central regions, each one a reservoir of gas and dust where stars may eventually form. Some of these clouds are famous in their own right: the Orion Molecular Cloud, the Taurus Molecular Cloud, the Carina Nebula, each contributing to our understanding of how matter organizes itself in space. Sagittarius B2 stands out even among this population, distinguished by its mass, its location, and above all by the richness of its molecular inventory. Comparing it to other clouds reveals what makes it unusual and what lessons it offers about chemistry in extreme environments. The Orion Molecular Cloud is perhaps the best-known star-forming region visible from Earth. Located roughly 1,500 light-years away, in a direction almost opposite to the galactic center, it produces the famous Orion Nebula, which is visible to the naked eye as a fuzzy patch below Orion's belt, and contains ongoing star formation that astronomers have studied in remarkable detail. The chemistry in Orion is complex, with many of the same molecules detected as in Sagittarius B2, though generally in smaller quantities relative to the cloud's total mass. Orion is closer and easier to observe, but Sagittarius B2 is larger, denser, and chemically richer. The Taurus Molecular Cloud represents a different kind of star-forming environment, more quiescent, less turbulent, producing primarily low-mass stars rather than the massive stars found in Sagittarius B2. Taurus lies about 500 light-years away, close enough that individual forming stars can be studied in exquisite detail, revealing the physics of collapse and accretion. The chemistry there is simpler than in Sagittarius B2, with fewer complex organic molecules detected, possibly because the lower levels of star formation provide less energy to drive complex reactions. Different clouds create different conditions for chemistry. Part of what distinguishes Sagittarius B2 is simply its mass, containing material equivalent to several million suns. It dwarfs most other molecular clouds in the galaxy. This large mass provides more raw material for chemistry, more surfaces for reactions to occur, and more time for complex molecules to accumulate before the cloud disperses. Larger clouds also tend to form more massive stars, which in turn provide more energy to heat the surrounding gas and liberate molecules from dust grains. Scale matters for chemistry as much as for star formation. The location near the galactic center also sets Sagittarius B2 apart, exposing it to conditions that clouds in the outer galaxy never experience. The cosmic ray flux is higher near the center, providing more energy to drive gas phase reactions that contribute to molecular complexity. The gravitational environment is more intense, potentially triggering star formation episodes that would not occur in quieter regions. Even the background radiation is different. The accumulated light of billions of central stars creates an energy bath that affects chemistry in subtle ways. Environment shapes outcome. Some molecular clouds contain very little complex chemistry at all, dominated instead by simple molecules like carbon monoxide and molecular hydrogen. These clouds are often younger, colder, or more isolated than the chemically rich ones, having not yet developed the conditions necessary for complexity to emerge. Sagittarius B2 represents the opposite extreme, a cloud that has had sufficient time, sufficient energy input, and sufficient raw material to build an extraordinary inventory of organic compounds. It sits at one end of a spectrum that other clouds occupy at various points. The comparison to clouds in other galaxies is more difficult because of the enormous distances involved, which limit the resolution and sensitivity of observations. Some nearby galaxies contain clouds that appear broadly similar to those in the Milky Way, suggesting that the same basic chemistry operates throughout the universe. A few extragalactic clouds show evidence of complex molecules, though detections are far less detailed than what is possible for sources within our own galaxy. Sagittarius B2 remains one of the best-studied molecular clouds anywhere, largely because it is close enough for thorough observation. What researchers learn from comparing clouds is that molecular complexity is not automatic. It requires specific conditions that not all clouds provide. A cloud needs dust grains to serve as reaction surfaces, cold temperatures to allow ices to accumulate, and periodic heating to release formed molecules into the gas phase. It needs time to let slow reactions proceed, protection from radiation that would destroy complex compounds, and sufficient mass to avoid rapid dispersal. Sagittarius B2 possesses all of these properties in abundance, which helps explain its exceptional chemical richness. The internal structure of the cloud also matters. The presence of multiple dense cores in various stages of star formation creates a range of conditions within a single cloud. Some regions are cold and quiescent, allowing ices to accumulate undisturbed, while others are warm and active, liberating molecules and driving further reactions. This diversity means that the cloud simultaneously hosts chemistry at many different stages, from initial grain surface reactions to gas phase processes in heated zones. The complexity of the cloud creates complexity in its chemistry. No two molecular clouds are identical, just as no two forests or no two coral reefs are identical. Each represents a particular history, a particular set of conditions, a particular outcome of processes that might have unfolded differently. Sagittarius B2 is the result of millions of years of specific circumstances, and another cloud with slightly different history might have developed differently. The molecules we detect there are not inevitable. They are the product of contingency, of events that happened rather than events that had to happen. This individuality makes the cloud scientifically valuable. The lessons from Sagittarius B2 extend beyond understanding a single cloud to understanding the galaxy as a whole. The organic chemistry developing there will eventually disperse, carrying molecules to new locations where they may participate in future clouds, future star formation, future planet building. The cloud is a node in a network of cycling material, not an isolated object, but a phase in a longer process. The next part will consider what this chemistry might mean for larger questions, specifically for the origins of the molecules that eventually became part of life on Earth. The molecules drifting through Sagittarius B2 bear an unmistakable resemblance to the compounds that constitute living things on Earth, built from the same elements and sharing the same basic structures. Carbon, hydrogen, oxygen, and nitrogen, the elements that dominate organic chemistry and biological systems, are the same elements that build alcohols, sugars, and acids in the cold darkness between stars. This correspondence is not coincidence. It reflects the fundamental properties of these atoms and the bonds they form, which operate identically whether on Earth or in a cloud 26,000 light-years away. The chemistry of life and the chemistry of space are connected at the most basic level. Amino acids, the building blocks of proteins, have not been definitively detected in Sagittarius B2, though the precursor molecules necessary to form them appear to be present. The cloud contains the raw ingredients from which amino acids could be assembled under the right conditions. Conditions that may exist in some regions of the cloud or in the environments of forming planetary systems. Whether the cloud actually produces amino acids remains an open question, one that future observations with more sensitive instruments may eventually answer. For now, the precursors are enough to suggest the possibility. Sugars like glycolaldehyde represent an even more direct connection to biochemistry. Since sugars form the backbone of DNA and RNA and provide energy for cellular metabolism, the detection of glycolaldehyde in Sagittarius B2 demonstrates that the universe can produce sugar molecules without any biological involvement whatsoever, assembling them through purely chemical processes on dust grains. More complex sugars remain undetected, but their absence may reflect the limitations of current technology rather than their true absence from the cloud. The simplest sugar being present suggests that the pathway to more complex sugars may be open. The question that naturally arises is whether material from clouds like this could have contributed to the chemistry that eventually became life on Earth. The solar system formed from a molecular cloud roughly 4.5 billion years ago, inheriting whatever molecules that cloud contained at the time of collapse. Asteroids and comets, remnants of that early period, still carry organic molecules, as confirmed by direct sampling of meteorites and by spacecraft observations. The connection is not speculative. It is a documented fact that primitive solar system bodies contain compounds similar to those in molecular clouds. Whether any specific molecule on Earth can be traced back to a specific cloud is impossible to determine. The material has been processed too many times, through too many environments, across too much time. What we can say is that the general categories of molecules, the types of chemistry, the building blocks of biology, appear to form universally wherever conditions allow. The cloud does not create life directly. It creates options, providing raw materials that might eventually participate in biological processes if the right environments exist. Life, if it arises, does not start from scratch. It inherits a chemical legacy from space. This idea that prebiotic chemistry occurs in molecular clouds has profound implications for how common life might be in the universe. If the ingredients of biology form everywhere, not just on planets with the right conditions, then life has more opportunities to emerge than we might otherwise expect. Every planetary system forms from a molecular cloud, and every molecular cloud contains organic compounds of some complexity. The question becomes not whether ingredients are available, but whether the additional conditions necessary for life, liquid water, energy sources, stable environments, are common or rare. The cloud cannot tell us whether life exists elsewhere in the universe, because the presence of organic molecules does not guarantee biological outcomes. Chemistry is necessary, but not sufficient. Life requires chemistry to organize in particular ways, to become self-sustaining, to reproduce and evolve. The gap between a cloud full of alcohols and a living cell remains vast, unbridged by any known natural process that we fully understand. But the cloud does tell us that the first steps in that journey occur naturally, without guidance, in conditions utterly unlike anything on Earth. What the cloud demonstrates is a kind of cosmic hospitality, the universe providing ingredients that life, should it emerge. The molecules in Sagittarius B2 do not care whether life exists or not. They form because physics and chemistry allow them to form, not because any outcome is intended. But that indifference makes the chemistry more remarkable, not less. Complexity arising without purpose, possibility created without plan, raw materials accumulating that may never be used for anything we would recognize as meaningful. The cloud is generous without knowing what generosity is. Some researchers speculate that the heavy bombardment period in the early solar system, when asteroids and comets regularly struck the young Earth, delivered significant quantities of organic material from space. These delivery events could have seeded the early oceans with molecules that terrestrial chemistry alone might not have produced, providing a head start for whatever processes eventually led to life. The idea remains debated. Some argue that Earth could have produced all necessary organics locally, but the cloud offers evidence that cosmic delivery is at least possible. The material exists, transport mechanisms exist. The question is only about quantities and survival. The emotional response to these ideas varies. Some find comfort in the thought that we are connected to the wider cosmos through shared chemistry, while others find the impersonal scale of it all somewhat cold. Both responses are valid, and neither is required by the science. What the cloud offers is simply information. Here is what exists, here is what forms, here are the implications for what might be possible elsewhere. Meaning is something we bring to the facts, not something the facts provide. What remains constant throughout these considerations is the cloud itself, continuing its slow work regardless of what we think about it or what questions we ask. The chemistry proceeds, the stars form, the molecules accumulate and disperse according to laws that operate without reference to human values. The next part will consider the timescales over which this work occurs, the deep time that stretches behind and before the cloud, connecting it to processes far older than any world currently existing. The molecules in Sagittarius B2 have been forming for longer than human civilization has existed. Longer, in fact, than humans have existed as a species. The processes that build complex chemistry in molecular clouds operate over tens of thousands to millions of years, accumulating results so slowly that no human observer could ever watch them occur in real time. When we detect alcohol in the cloud tonight, we are seeing the product of reactions that began when mammoths still walked the earth, or earlier. The chemistry is patient in ways that human experience cannot easily encompass. The cloud itself is older than its current molecular inventory, having formed from gas that was already circulating through the galaxy, long before it gathered into this particular structure. Estimates suggest that Sagittarius B2 has existed as a coherent feature for several million years, though its exact age is difficult to determine precisely. During that time, it has been gradually condensing, heating in some regions, cooling in others, forming stars that alter its internal conditions. The cloud is not static, it is evolving, though on timescales that make it appear frozen to human observers. The atoms that compose the molecules in the cloud are older still, forged in the cores of stars that lived and died before the sun ever formed. Carbon, nitrogen, oxygen, the elements of organic chemistry, are all produced through nuclear fusion in stellar interiors, then distributed through space when those stars explode or shed their outer layers. The carbon in the alcohols of Sagittarius B2 may have been created billions of years ago in stars that no longer exist, circulating through the galaxy until it happened to accumulate in this particular cloud. Every molecule carries a history that stretches back beyond what we can individually trace. The timescales of molecular cloud evolution connect to timescales even larger. The age of the galaxy itself, the age of the universe, the span from the Big Bang to the present. The Milky Way is roughly 13 billion years old, and for most of that time, molecular clouds have been forming, dispersing, and reforming in cycles that continue to this day. Sagittarius B2 is simply the current expression of processes that have repeated countless times, in countless locations, since the first generations of stars began producing the heavy elements necessary for complex chemistry. The cloud is ancient in human terms, but young in cosmic terms. Star formation within the cloud occurs on timescales measured in hundreds of thousands to millions of years, beginning with slow gravitational collapse and ending with nuclear ignition in stellar cores. The young stars currently forming in Sagittarius B2 will continue to develop for millions of years more, gradually clearing away the surrounding gas and dust as they stabilize. Some of the most massive stars may complete their entire life cycles within a few million years, dying in explosions that enrich the galaxy with newly forged elements. The cloud hosts both birth and impending death, separated by spans of time that dwarf any human lifetime. The future of the cloud is written in the physics of gravity, radiation, and motion, though predicting specific outcomes remains beyond current capability. Over the next several million years, star formation will likely continue, gradually consuming the cloud's mass and dispersing its material into the broader galaxy. Some portion may survive long enough to participate in future cloud formation, cycling back into dense regions where the process can begin again. The cloud is not permanent, it is a phase, a temporary organization of matter that will eventually dissolve. Nothing about these timescales should inspire urgency or anxiety. They simply describe how the universe operates, indifferent to human concerns or human schedules. The cloud will continue its slow evolution whether we observe it or not, whether we understand it or not. The molecules will form, the stars will ignite, the matter will cycle through the galaxy, following laws that do not require our attention. This continuity can be understood as reassuring or humbling, depending on perspective, but it is simply factual in either case. What deep time offers is context for understanding why the chemistry in Sagittarius B2 is complex, despite occurring in cold, low-density environments. The reactions may be slow, but they have been running for so long that even slow accumulation produces substantial results. A process that adds one molecule per year will, over 1 million years, produce 1 million molecules. And the cloud has had more than enough time for such accumulation to occur. Patience compensates for efficiency, and the universe has nothing but patience. The light from the cloud that reaches our telescopes tonight began its journey approximately 26,000 years ago, during the last ice age on Earth, when glaciers covered much of the northern continents. In that time, the light has traveled without interruption, crossing the vast emptiness between stars, while human civilizations rose and fell on a small planet it would never approach. The observation of the cloud is itself a kind of time travel. We see the past, preserved in light that has taken longer to arrive than any human artifact has existed. The present does not exist for objects so far away. The concept of simultaneity breaks down across such distances, becoming meaningless in any practical sense when applied to objects separated by tens of thousands of light years. What we call now for Sagittarius B2 is actually a reconstruction, a guess based on physical models that predict how the cloud has changed since the light we observe departed. The cloud we study is a ghost of something that may have already evolved substantially, though we cannot know for certain until future light arrives. Observation and reality are permanently out of sync at these scales. Human beings evolved to perceive time in rhythms of days, seasons, and generations, spans that feel natural because they match our biology and our social experience. The timescales of molecular clouds exceed these intuitive durations by factors of thousands or millions, placing them beyond direct comprehension in any emotional sense. We can calculate the numbers, write them down, compare them to other numbers, but we cannot truly feel what a million years means because nothing in our experience provides a reference point. The mind accepts the information without fully absorbing it. This disconnect between human time and cosmic time is not a failure of understanding. It is simply a feature of being small, brief creatures in a large, old universe. The cloud does not care whether we can comprehend its duration. It simply persists according to the physics that governs its behavior. Our inability to grasp deep time intuitively does not make it less real, any more than our inability to see radio waves makes them less present. The universe operates on its own terms, and we observe what we can. The formation of a single alcohol molecule in the cloud might take years, occurring through a sequence of chance encounters on the surface of a dust grain floating in darkness. That molecule might then persist for thousands of years more, drifting slowly through the cloud, occasionally colliding with other molecules, occasionally being broken apart by radiation. Its existence is a statistical outcome of countless small events, none of which were directed or planned, all of which were governed by probability. The molecule is patient because it has no choice. Patience is simply what slow processes look like from the outside. When we speak of the cloud forming stars rapidly, we mean within a few 100,000 years, a duration that sounds long but is brief by astronomical standards. A star like the Sun takes roughly 10 million years to fully contract and stabilize, beginning from the initial collapse of a dense core and ending with sustained nuclear fusion. The massive stars in Sagittarius B2 form faster because their gravity is stronger, compressing their cores more efficiently, but even they require timescales far beyond human planning. Rapid in this context means merely less slow. The chemistry of the cloud will continue long after the current generation of stars has formed and dispersed the surrounding material. Some molecules will be destroyed by stellar radiation. Others will be incorporated into protoplanetary disks around young stars, potentially ending up on planets or moons. The alcohol that exists in the cloud today may, millions of years from now, be part of a comet, an asteroid, or an ocean on a world we cannot imagine. The future is not separate from the present. It is already unfolding, too slowly for us to notice. Deep time dissolves the boundaries between past, present, and future, revealing them as human categories imposed on a continuous flow of change. The cloud does not experience these distinctions. It simply exists, moment by moment, each moment lasting millions of years by human reckoning. What we call history is a brief flash in this ongoing process, a thin slice of time containing everything we have ever known. The cloud predates our history and will outlast it, continuing its slow work regardless of what happens on any particular planet. There is comfort available in this perspective, if one chooses to accept it. The comfort of knowing that the universe contains processes far larger and longer than human concerns. The anxieties of daily life dissolve against a backdrop of millions of years, not because they are unimportant, but because they are brief. The cloud offers scale, a reminder that existence extends far beyond any individual experience or any collective memory. What feels permanent to us is transient to the cosmos. The molecules in the cloud tonight are part of a story that began billions of years ago and will continue billions of years into the future, cycling through stars, clouds, planets, and space. We happen to be observing one small chapter, one particular moment, one arrangement of matter that will soon, in cosmic terms, give way to another. The observation itself is part of the story, a brief interaction between distant matter and curious minds, separated by unimaginable spans of time and space. We are participants, however briefly, in something very old. This is simply how the universe works, neither welcoming nor hostile, neither meaningful nor meaningless in any human sense. The cloud is there because physics allows it to be there, and the molecules form because chemistry permits their formation. Deep time is the medium in which these processes occur, the canvas on which slow events paint their gradual patterns. Understanding this requires no special wisdom, only attention, and the willingness to accept what the evidence reveals. The next part of our journey considers what remains unseen, the molecules and processes that may exist in the cloud, but have not yet been detected by our instruments. The catalogue of molecules detected in Sagittarius B2 is extensive, including over 50 distinct chemical species identified through decades of radio observation. This number is impressive by the standards of astronomical chemistry, representing one of the richest molecular inventories found anywhere in the galaxy. However, the catalogue is almost certainly incomplete, limited by the sensitivity of our instruments and the physics of molecular emission. What we have found is likely only a fraction of what exists. Molecular detection depends on signals strong enough to distinguish from background noise, produced by species abundant enough to emit or absorb measurable quantities of radiation. Rare molecules, or molecules that emit weakly at radio frequencies, may be present in the cloud without ever appearing in our data. The absence of a detection does not mean the absence of a molecule. It means only that we have not yet found evidence for it. The distinction matters, especially when considering what the cloud might actually contain. Some molecules predicted by chemical models have never been detected in any interstellar cloud, despite theoretical reasons to expect their presence. These species may exist in quantities too small to observe, or they may emit at frequencies that current telescopes cannot access efficiently. Others may be destroyed too quickly after formation to accumulate in detectable amounts, existing only briefly before radiation or collisions break them apart. The cloud's chemistry may be richer than we know, hidden behind observational limitations. Amino acids represent a particularly tantalizing category of molecules that might exist in Sagittarius B2, but have not been confirmed. The simplest amino acid, glycine, has been claimed in various interstellar observations, but the detections remain controversial, with some researchers questioning whether the signals truly originate from glycine or from other species. If amino acids do form in molecular clouds, they would represent a direct link between interstellar chemistry and the chemistry of life, but proving their presence requires stronger evidence than currently available. The question remains open. The precursors to amino acids are clearly present in the cloud. Molecules like methylamine and acetic acid that could combine under the right conditions to form more complex structures. Whether those conditions exist and whether the products survive long enough to accumulate depends on factors that remain poorly understood. Laboratory experiments suggest that amino acids can form on dust grain surfaces exposed to radiation, but extrapolating from laboratory conditions to cloud conditions involves uncertainties. The chemistry is plausible, but not proven. Larger organic molecules, containing 10 or more atoms, become increasingly difficult to detect because their emission is spread across many frequencies, diluting the signal at any single frequency. Some large molecules have been found in interstellar clouds, polycyclic aromatic hydrocarbons, for example, but many others remain beyond current detection capabilities. Sagittarius B2 may contain complex organics that we cannot see, molecules that would change our understanding of interstellar chemistry if we could identify them. The possibility persists without confirmation. New telescopes and new techniques gradually push the boundaries of detection, revealing molecules that were previously invisible. The Atacama Large Millimeter Array, a collection of radio dishes in the Chilean desert, has already discovered several new interstellar molecules since its completion, including some in Sagittarius B2. Future instruments will continue this work, adding to the catalogue slowly but steadily over coming decades. Each discovery revises our picture of what molecular clouds contain. The molecules we cannot detect are not necessarily exotic. Some may be common species that happen to emit at frequencies outside our observational windows. Water, for example, is difficult to observe from Earth's surface because atmospheric water vapor absorbs the same frequencies, requiring space-based telescopes to study effectively. Other molecules may face similar challenges, hidden not by rarity, but by the limitations of observing through Earth's atmosphere. Orbital observatories offer solutions, but they are expensive and limited in number. Isotopic variants of known molecules add another layer of complexity to the unseen chemistry of the cloud. A molecule containing a rare isotope of carbon or oxygen emits at slightly different frequencies than the common version, requiring separate observations to detect. These variants are intrinsically less abundant, making them harder to find, but they provide important information about the chemical history of the cloud. Some isotopic species have been detected in Sagittarius B2. Many others likely exist without being catalogued. The physical structure of the cloud also hides information, with dense cores potentially containing chemistry that differs from the more diffuse outer regions. Observations typically sample the entire line of sight through the cloud, blending together emissions from regions with different temperatures, densities, and chemical compositions. Separating these contributions requires sophisticated modeling and high-resolution observations, both of which remain works in progress. The cloud's interior may be chemically distinct from what we observe in aggregate. Dust itself may carry molecular information that we cannot easily access, with complex organic molecules locked onto grain surfaces rather than floating freely in the gas. These surface-bound species do not emit in the same way that gas phase molecules do, making them effectively invisible to standard radio observations. Indirect evidence for surface chemistry comes from laboratory experiments and from observations of ices on grains, but the full inventory of dust-bound molecules remains unknown. The grains keep their secrets. Time-dependent chemistry adds another dimension to what remains unseen. Molecules that form briefly during particular phases of cloud evolution then disappear before they can be observed. A passing shockwave, a burst of radiation from a forming star, or a temporary increase in temperature could trigger chemical reactions that produce short-lived species never seen under normal conditions. These transient molecules may play important roles in the overall chemistry of the cloud without ever appearing in our catalogues. The cloud's history is not fully written in its current state. Negative ions, molecules, carrying an extra electron rather than a positive charge, were long thought too unstable to exist in interstellar space until they were detected in molecular clouds several years ago. Their discovery surprised many researchers and prompted revisions to chemical models that had not included them. Similar surprises may await in Sagittarius B2, with molecular species that current theories do not predict, but that nonetheless exist under the unusual conditions of the cloud. The unexpected remains possible. The observational challenge is not merely technological, it is also intellectual, requiring researchers to know what to look for before they can find it. Searching for a new molecule means predicting its spectral signature, calculating the frequencies at which it should emit, and then looking for those specific signals in the data. Molecules that no one has predicted may exist in plain sight, their emissions misidentified or ignored because observers do not recognize what they represent. The catalogue is shaped by human expectations as well as by instrumental capabilities. What we know about the cloud is therefore provisional, subject to revision as observations improve and as theoretical models become more sophisticated. The current picture is accurate as far as it goes, but it does not go as far as the reality it attempts to describe. Humility is appropriate when considering the limits of our knowledge, not because the science is flawed, but because the universe is large and our observations are necessarily incomplete. The cloud contains more than we can see. This incompleteness is not frustrating. It is simply the condition of scientific inquiry, the recognition that every answer opens new questions and every discovery reveals new mysteries. The molecules we have found are real and significant. The molecules we have not found are equally real, waiting in the dark for instruments sensitive enough to reveal them. The cloud is patient, and the universe does not hurry to disclose its contents. What remains unseen will, in time, become visible. The next part of our journey considers the long future of Sagittarius B2. What will become of the cloud, its molecules, and its forming stars over the millions of years ahead? Sagittarius B2 will not exist forever, though its end lies millions of years in the future, far beyond any human planning or concern. The processes currently occurring within the cloud, star formation, radiation, gravitational collapse, will eventually consume its mass and disperse its material into the broader galaxy. What exists now as a coherent structure will become, in time, a scattered collection of stars, dust, and gas, no longer recognizable as a single object. The cloud is temporary, though its timescale of temporariness exceeds human imagination. Star formation is the primary mechanism driving the cloud's eventual dissolution, converting dense gas into compact stellar objects that no longer participate in cloud chemistry. Each star that forms removes mass from the cloud permanently, locking matter into a gravitational well from which it will not easily escape. The massive stars currently forming in Sagittarius B2 will, over the next few million years, continue this process, gradually depleting the reservoir of gas and dust. The cloud is feeding its own transformation. Radiation from newly formed stars accelerates the dispersal process, heating surrounding gas and driving it outward into regions of lower density. The most massive stars produce intense ultraviolet radiation that ionizes nearby hydrogen, creating expanding bubbles of hot plasma that push against the cold molecular material. These bubbles grow over time, merging and overlapping, eventually clearing large cavities in the cloud structure. The stars consume the cloud that created them. Stellar winds carry additional energy into the cloud environment, streams of charged particles flowing outward from young stars at hundreds of kilometers per second. These winds collide with cloud material, transferring momentum and energy, compressing some regions while dispersing others. The interaction between winds and cloud creates complex structures, pillars, filaments, shells, visible in observations of other star-forming regions. Sagittarius B2 is likely undergoing similar reshaping, though the details depend on which stars have formed and where. The most dramatic events in the cloud's future will be supernova explosions, occurring when the most massive stars exhaust their nuclear fuel and collapse. A single supernova releases more energy in seconds than the Sun produces over its entire lifetime, sending a shockwave through surrounding material at thousands of kilometers per second. Any portion of Sagittarius B2 within a few tens of light years of such an explosion will be profoundly affected, heated, compressed, possibly triggered into additional star formation. The cloud's future includes these violent episodes, though they will occur millions of years from now. Supernova explosions also enrich the cloud with newly forged heavy elements, scattering iron, nickel, silicon, and other species into the surrounding gas. These elements mix with existing cloud material over thousands of years, becoming available for incorporation into future generations of stars and planets. The destruction of massive stars is also a creative process, adding complexity to the chemical inventory of the galaxy. What ends in explosion continues in new forms. The molecules currently in the cloud face varied fates, depending on where they reside and what events occur nearby. Some will be destroyed by radiation, their chemical bonds broken by ultraviolet light or cosmic rays, returning their atoms to simpler forms. Others will survive, drifting through regions of the cloud that remain shielded from intense radiation, persisting for millions of years in cold darkness. Still others will be incorporated into forming planetary systems, carried by gas and dust into the disks surrounding young stars. The alcohol in the cloud tonight may, in some distant future, become part of a world. Planetary systems forming from cloud material inherit its chemical complexity, beginning their existence with a supply of organic molecules already present in their birth environment. Observations of protoplanetary disks have confirmed that complex molecules survive the transition from cloud to disk, appearing in the same locations where planets are expected to form. What began as interstellar chemistry can become planetary chemistry, then potentially biological chemistry if conditions permit. The continuity is remarkable. Comets and asteroids serve as delivery mechanisms, carrying organic molecules from the outer reaches of planetary systems to inner worlds where liquid water may exist. Earth's early history almost certainly included such deliveries, with impacts depositing organic material that may have contributed to the origin of life. If this process is common, if it occurs wherever stars form from molecular clouds, then clouds like Sagittarius B2 may be seeding future biospheres across the galaxy. The connection is speculative, but grounded in observed chemistry. The gas that is not converted into stars or incorporated into planetary systems will eventually drift away from the cloud, mixing with the general interstellar medium over millions of years. This diffuse gas carries molecules with it, spreading the products of cloud chemistry through the galaxy in a slow, gradual process. The cloud's influence extends beyond its boundaries, contributing to the chemical evolution of the Milky Way as a whole. Nothing is truly lost, only redistributed. Over hundreds of millions of years, the dispersed material from Sagittarius B2 may participate in the formation of new molecular clouds, drawn together again by gravity in distant regions of the galaxy. The cycle of cloud formation, star birth, and dispersal is ongoing, repeating countless times since the galaxy's youth. The atoms that compose the cloud have likely passed through this cycle multiple times already, residing in previous clouds, previous stars, previous planets. The cloud is one iteration of a very old pattern. The galaxy itself is slowly evolving, though on timescales even longer than cloud lifetimes. The rate of star formation across the Milky Way has declined since its early history, and will continue to decline as available gas is gradually consumed. Eventually, perhaps trillions of years from now, the galaxy will contain too little gas to form new stars at all, and molecular clouds like Sagittarius B2 will become impossibilities. This far future is too distant to contemplate meaningfully, but it provides context for the present. Clouds exist now because the galaxy is still young enough to create them. The cloud's future is written in physics, but not in detail, determined by laws that operate reliably but applied to initial conditions too complex to track precisely. We cannot predict exactly which stars will form where, exactly when supernova explosions will occur, exactly which molecules will survive and which will be destroyed. The general trajectory is clear. The specifics remain uncertain. The cloud's future is knowable in outline and unknowable in particulars. What we observe tonight is a snapshot, a single frame from a very long movie that began millions of years ago and will continue millions of years hence. The cloud appears static in our observations because human lifetimes are too short to perceive its motion. But the motion is real nonetheless. Stars are forming, gas is flowing, molecules are being created and destroyed, gravity is pulling, radiation is pushing. The cloud is busy in its slow way. None of this activity requires our attention or our understanding to continue. The cloud will evolve according to its own dynamics, indifferent to human observation, following paths determined by physics rather than purpose. Our role is simply to watch, to record, to try to understand what we can with the limited tools and time available to us. The cloud does not need us, but we are richer for knowing it exists. The next part of our journey returns to the present moment, to the cloud as it exists tonight. Still there, still forming stars, still building molecules, carrying on its long work in the dark. Sagittarius B2 is still there. Tonight, as it was last night, as it will be tomorrow night. A vast presence near the center of the galaxy, continuing its slow work without interruption. The cloud does not pause for human observation. It does not speed up or slow down, based on whether anyone is watching. The processes occurring within it, molecular formation, gravitational collapse, stellar ignition, proceed according to their own timescales, indifferent to any awareness outside themselves. The cloud simply is, regardless of who knows it. The radio signals from the cloud are arriving continuously, crossing the distance from the galactic center and reaching Earth's atmosphere in a steady stream that never stops. Telescopes pointed at the right frequencies receive these signals night after night, recording the same spectral signatures, the same molecular fingerprints, the same evidence of alcohol and sugar and acid drifting in the dark. The data accumulates slowly, adding detail to pictures that are already decades in the making. The observation is ongoing. The astronomers who first detected alcohol in the cloud are mostly retired now or passed away. Their work continued by new generations who inherited both the telescopes and the questions. Science proceeds this way, each generation building on what came before, extending the record, refining the understanding, passing the work forward to those who follow. The cloud has been studied for longer than some of its current observers have been alive. It will be studied long after they are gone. The molecules in the cloud tonight are essentially the same molecules that were there when observations began, with changes too slow to detect over human timescales. New molecules have formed, certainly, and old ones have been destroyed. But the overall composition has shifted only slightly over the decades of human attention. The cloud's chemistry is stable in the short term, evolving only over spans of time that dwarf any research program. What we see now is what we saw before, and what we will see for as long as we continue looking. The stars forming within the cloud are also essentially unchanged from human perspectives. Their growth too gradual to measure directly over years or decades. A protostar that was dense 10 years ago is slightly denser now, slightly closer to ignition, but the difference is too small to photograph or quantify. The changes are real but invisible to short-lived observers, occurring beneath the threshold of what our instruments can detect on human timescales. The cloud's activity is hidden by its own slowness. This stability is reassuring in its own way. The knowledge that something vast and ancient continues without needing our intervention or our concern. Human life is filled with urgency, with deadlines, with the sense that time is running out, but the cloud operates under no such pressure. It has millions of years to form its stars and build its molecules. It does not hurry because hurrying would make no difference. The cloud's patience is total, built into the physics that governs its behavior. The distance between Earth and the cloud is itself a kind of buffer, isolating us from whatever occurs there by 26,000 years of light travel. Nothing that happens in Sagittarius B2 tonight will affect Earth in any way we could detect. Nothing that happens on Earth tonight will affect the cloud. The separation is absolute, enforced by the finite speed of light and the vast emptiness of interstellar space. We are connected only by observation, by the information carried in electromagnetic radiation. The information we receive is old, showing us a cloud that existed before human civilization began, before agriculture, before written language. The light departed when the last ice age was ending, when the climate was shifting, when humans were just beginning to spread across the continents. Everything that has happened since, every empire, every discovery, every thought, occurred while that light was in transit, crossing the galaxy in silence. The observation is a kind of time travel, a glimpse of the distant past preserved in radiation. The cloud does not know it is being observed, of course, having no awareness, no perspective, no experience. The molecules that compose it are not conscious. The stars that form within it have no feelings. The chemistry that occurs is mechanical, following rules that operate without intention or purpose. What we call knowing or understanding exists only on our side of the observation, in minds that evolved on a small planet far from the galactic center. The cloud is simply matter, arranged in patterns that happen to interest us. This does not diminish the cloud or make it less worthy of attention. It simply clarifies the relationship between observer and observed, between knower and known. We bring meaning to the observation. The cloud provides only the facts. The arrangement is appropriate, perhaps even comforting, because it places the responsibility for understanding where it belongs. With us, the ones who ask the questions in the first place. The cloud answers by existing. We must interpret what its existence means. The alcohol in the cloud is still there, forming slowly on dust grains, drifting through the cold darkness, waiting for nothing because waiting implies expectation. The glycolaldehyde is still there, the simplest sugar, carrying no sweetness in the vacuum, tasting of nothing because taste requires tongues, and the cloud has none. The ethyl formate is still there, the molecule that gives raspberries their scent on Earth, producing no fragrance in space because fragrance requires noses and atmosphere. The molecules exist without the experiences we associate with them. The cloud's existence is independent of any meaning we assign to it, continuing whether we find it fascinating or boring, significant or trivial, beautiful or indifferent. Our responses are our own, projections of human minds onto non-human phenomena, attempts to make sense of something that operates beyond any scale we can directly experience. The cloud does not need our admiration does not change the cloud. What we feel is real, but it lives in us, not in the object of our feeling. Tonight, if the sky is clear, and if you have access to a radio telescope, which almost no one does, you could point it toward the constellation Sagittarius and receive signals from the cloud yourself, photons that have traveled for 26,000 years to reach your detector. The signals would be faint, requiring careful amplification, mixed with noise from countless other sources, but they would be there, as they have been there for longer than humans have known how to look. The cloud broadcasts continuously to anyone who cares to listen. Most people will never hear those signals directly, never see the spectra that reveal the cloud's chemistry, never process the data that astronomers analyze in their research. For most people, the cloud exists only as an idea, a fact learned from a video or a book or a conversation. Accepted on trust because the evidence is too specialized to evaluate independently. This is fine. This is how knowledge works, distributed across communities, held in common by people who rely on each other for accuracy. The cloud is real whether or not any individual can prove it personally. What remains after all the facts have been presented and all the explanations have been offered is simply the cloud itself, a massive structure near the galactic center, rich in organic molecules, forming stars, evolving slowly, carrying on. The cloud does not conclude, it continues. The story we have told is necessarily incomplete, limited by what we know and what we can express in language, bounded by the frames of this particular telling. The cloud exceeds any description. The cloud is there, still there, will be there, doing what clouds do. Being massive, being cold, being chemically active, being gravitationally unstable in the ways that lead to star formation. The cloud is indifferent to endings because endings are human artifacts, ways of organizing narratives that do not apply to ongoing processes. There is no final statement because the cloud is not final. There is no conclusion because the cloud does not conclude. There is only continuation stretching into a future we will not see. If you are still awake, if you are still listening, if these words are still reaching you, the cloud is there. If you are drifting towards sleep, if your attention is fading, if the words are becoming distant, the cloud is still there. If you are already asleep, if this narration has become background sound, if your mind has turned elsewhere, the cloud remains exactly where it was. The cloud does not depend on your awareness. The alcohol drifts. The stars form, the molecules accumulate, the light travels, the cloud endures. And that is simply how things are tonight, in the quiet spaces between the stars, where chemistry continues without witnesses, where time moves without hurry, where the galaxy carries on its ancient work. The cloud asks nothing of you. The cloud offers nothing but itself. The cloud is there, and you are here, and the distance between is vast and dark and filled with light, too old for human history. Rest now, if you like. The cloud will still be there when you wake.